Hello everyone, welcome to all in this video lecture series of Database Management System. I am Deepak Aneja, Assistant Professor ABS Engineering College, Ghaziabad. Today in this video, we will do the practice questions on decomposition. In the previous lecture, we have already understand the concept of decomposition. Now in this video, we will cover the practice question on decomposition. So question number 1, consider the universal relation are A, B, C, D, E, and the set of FDs given are AB determines C and D determine E. Now decompose the relation R into 2NF. So in this question, when we do the decomposition, we will start the decomposition from first 2NF because by default our uh, table is in 1NF. Then we start from 2NF, then 3NF, and in the last BCNF. We will decompose the table. Now, the given FDs, first we have to find out the candidate key. Here, C is already from the right-hand side attribute. C and E. Missing attributes are A, B, and D. We have to take the closure set of A, B, D. From AB, we can determine A, B, D. And from AB, we can determine C. And from D, we can determine E. All the attributes are determined by A, B, D. So the candidate key is A, B, D. Now, step 2, prime attributes who are the part of candidate key. Those attributes are prime attribute A, comma B, comma D, and non-prime attributes are C and E. Now, given functional dependencies are AB determines C and D determine E. Now we have to check, is these functional dependency in 2NF or not? Now the condition to check 2NF, the left hand side should be the proper subset of candidate key and right hand side should be the non-prime attribute. This is the condition for partial dependency, or there should be no partial dependency. Now check for this. AB is the part of proper subset of candidate key, true, and C is non-prime attribute, true. So here is output is true. Then here is partial dependency exists. So this is not in 2NF. Now here, check for this part D, A, B, D. Yes, this is true. And E is non-prime attribute, true. So this is also in 2N, not in 2NF. Now we have to decompose the table up to 2NF. So there is a relation R. Then break, decompose in R1. So in R1, first attribute is ABC. A, B, C. We will break this first functional dependency. So AB determine C. Now we have to check, is there any other functional dependency that will start from A, B, or C? So there is no other functional dependencies that will start from either A, either or B or C. So this is the one decomposed table. Attributes are R1, attributes are A, B, and C. Now we will check for this table, the candidate key is AB. So there is no partial dependency exists. So this is in 2NF. Now this decomposed table is in 2NF. Now R2, second functional dependency is DE. Attributes are D or E. So here the functional dependency comes as D determines E. In this, we have to check, is this table is in 2NF or not? So here the candidate key is D. So here no partial dependency exists. So this is also in 2NF. In the last, we have to create one more table or relation of candidate key. So the candidate key are A, B, D. Now the decomposition of a relation R up to 2NF is R1, R2, and R3. Attributes of R1 are A, B, C, and R2 is D, E, and in the last R3 relation A, B, D. Now let us try one more example. Consider the relation R A B C D E F G H I J, and the set of FDs are AB determine C, AD determine GH, BD determine EF, A determine I, S determine J. Decompose the relation R into 2NF. So first step, we have to find out the candidate key. Now the candidate key is C, G, H, E, F, I, J. The missing attributes are A, B, D, A, B, D. Now take the attribute closure of A, B, D, A, B, D, and from AB we can determine C, from AD we can determine GH, from BD we can determine EF, or from A we can determine I, or from H we can determine J. A, B, C, D, E, F, G, H, I, J. We can determine all attributes. So the candidate key is A, B, D. So the prime attributes are A, B, and D, and non-prime attributes are C, E, F, G, H, I, and J. Now take all the functional dependency. AB determines C, AD determine GH, BD determine EF, A determine I, and H determine J. Now check, is this relation is in 2NF or not? Condition is left hand side should be the left hand side should be the proper subset of candidate key, and right hand side should be the non-prime attribute. This is the condition for partial dependency. Now check for this. AB is the proper subset, true, and C is non-prime attribute, true. So this is true. Here is partial dependency exists. So this is not in 2NF. Now AD determine G. AD is true, and GH. GH both are non-prime attribute. This is true. So this is also in not in 2NF. BD, this is true, and EF both are non-prime attributes. So this is not in 2NF. A determine I. A is the proper subset of ABD, true, and I is non-prime attribute. This is true. So this is also is not in 2NF. Now check for H. H, this is false, and J is true. So this is false. So this functional dependency is in 2NF. Now, first we will decompose a relation R into first R1. So R1, AB determines C. A, B, C. Now A, B, C. From A, So from A, we can determine I. So we can include here I. And from B, we cannot determine anything else. And C, from we cannot determine anything else. So here the functional dependencies come. AB determines C and A determine I. Now here the for this table the candidate key is AB. So this functional dependency is in 2NF, but here the uh, partial dependency exists. So this is not in 2NF. So that's why we cannot we cannot uh, take take this A determines I functional dependency in the relation R1. So the R1 is A, B, C. Decomposed table R1 is A, B, C. So the functional dependency is AB determines C. Now this relation is in 2NF. Now decompose further. Now take this AI. A determine I. Now the candidate key here is A. So this is in 2NF. Now R3 is a relation AD determine GH. AD GH. So here from A we cannot determine anything else that is left. AI we already decompose into a different table. GH there is no here H determines J. So we can include H determine J in this table. So the functional dependency for R3 table is AD determine GH and H determine J. So here the candidate key is AD. Now this is in 2NF because this is the candidate key. Now HJ. H is not the proper subset, so no partial dependency exists in this. So this is also in 2NF. So we can collaboratively take both functional dependency into one table. So R3 is ADGHJ. Now this and this is cancel out. Now BD. R4 we will take B, D, E, F. B, D, E, F. So here functional dependency is BD determines EF. So this is also in 2NF, or in the last R5, we will take the candidate key. One table, one decomposed table is of candidate key A, B, D. Now the decomposition of R into R1, R2, R3, R4, and R5. In R1, attributes are A, B, C. In R2, attributes are AI. In R3, attributes are A, D, G, H, J. And in R4, attributes are B, D, E, F. And in R5, A, B, D. So this is the decomposition of a relation R into 2NF. Now let us take one more example. Consider the universal relation R, A, B, C, D, E, and the set of FDs. F, A determine B, and B determine E, and C determine D. Decompose the relation into 3NF. Now we have to decompose the relation into 3NF. The same procedure. First, we have to find out the candidate key. Now, B, E, and D. Missing attributes are AC. Take the attribute closure of AC. AC from A we can determine B, from B we can determine E, and from C we can determine D. So all the attributes. So the candidate key is AC. Now prime attribute are A, comma C, and non-prime attributes are B, D, and E. Now take the given functional dependency AB, BE, and CD. Here we will directly decompose the relation into 3NF. Now check the given functional dependency for 3NF. Now three condition for to check the given functional dependency is in 3NF or not. Left hand side should be the candidate key or super key, or right hand side should be the prime attribute. There should be no partial dependency. Sorry, no transitive dependency exists. There should be no transitive dependency in case of 3NF. Now, left hand side is the candidate key. No, this is false. Or B is the prime attribute. False. So this is not in 3NF. Now B is the candidate key. False. Or E is prime attribute. False. This is not in 3NF. C is not the candidate key. False. Or right hand side D should be the prime attribute. False. So this is also not in 3NF. Now decompose the table R relation into first R1. First is AB. Now AB. From B we can determine E. From B we can determine E. So we will take this functional dependency into a single table ABE. So here the functional dependency exists AB and B determine E. So here we can see that there is transitive dependency. A determine B and B determine E. Or we will check candidate key is A and this is in 3NF, but this is not in 3NF. So we will further decompose this relation into R11 and R12. Here is AB or here is BE. Functional dependency comes AB in A determine B and for B, B determine E. Then this and this goes. Now R2, C and D. Functional dependency is C determine D. Here the candidate key is C. Now this is the candidate key. Left hand side is the candidate key. So this functional dependency comes under 3NF. Now there is one more decomposition. R3 is of candidate key. Candidate key is AC. So the decomposition of R into R1, R2 and R3. R1 is ABE. This is further decomposed into R11 and R12. Attributes are AB and here is BE. In R2, attributes are CD and in R3, attributes are A3. So I hope you will understand the concept. Now let us take one more example of 3NF, decomposition of a relation R into 3NF. Now the same procedure. First of all, we will find the candidate key. Now C, D, E, F, G, H, I, J. The missing attributes are A, B. Take the attribute closure of A, B to C, from A to D, E, from B to F, F to G, H, D to I, J, A, B, C, D, E, F, G, H, I, J. So the candidate key is A, B. Now the prime attributes are A, comma B, and non-prime attributes are C, D, E, F, G, H, I, J. Now take the functional dependencies. AB determines C, A determine DE, B determine F, F determine GH, and D determine ij. Now check for 3NF. Left hand side should be the candidate key, AB true. So this is in 3NF. This is in 3NF. Now left hand side should be the candidate key, false, or DE is the prime attribute, false. So this is not in 3NF. A, B, sorry, B, F. Left hand side should be the candidate key, false, or F is the prime attribute, false. This is not in 3NF. F, false, or GH, both are non-prime, so false. This is not in 3NF. D is not the candidate key, false, or IJ are the non-prime attribute, false. This is not in. Now, let us start to decompose the table. R is a relation and decompose R1. This is in 3NF, so let us start from ADE. ADE. Now, ADE from A, we cannot have now from D, D to IJ. So DIJ. Further, there is no this and this functional dependency. Now, the functional dependencies are ADE and D determine IJ. Here, the candidate key is A. So this is in 3NF, but this here is false or IJ are false. So this is not in 3NF. Now, further, we will decompose this relation into two, R11, R12. Here the attributes are ADE, and here the attributes are DIJ. Now, ADE. Now, this is in 3NF, or here is DIJ. Now, this is in also in 3NF. Now, R2, B determines F, BF, and from F, GH. Functional dependencies are BF and FGH. Now the candidate key is B. So this is in 3NF, but this is not in 3NF. Now further, we will decompose this relation into R21 and R22. Here BF and into to FGH. The functional dependency here comes as BF and F determine GH. Now this is in 3NF, or this is also in 3NF. We are doing this because we have to decompose the relation into 3NF. So that's why we are here checking for 3NF. Now these are cancelled out. Now in the last, there is R3, A, B, C. This is for the candidate key. So AB is the candidate key and ABC is the super key. We will include this ABC attributes in the relation R3. So the decomposition of R into R1, R2, and R3. R1 is A, D, E, I, J, and further this will decompose into R11, R12. Attributes are A, D, E, and D, I, J. For R2, attributes are B, F, G, H, and further we will decompose R21, R22. For 21, attributes are B, F, and for R22, F, G, H. Now in R3, the attributes are A, B, C. I hope you will understand the concept. Now, the practice questions on lossless and lossy joint decomposition. We have already studied the concept of lossless and lossy joint decomposition. The after decomposition, when we join the decomposed table, so the decomposition should be lossless. So there are three conditions we have already studied, that R1 union R2, that must be equals to R. Second, R1 intersection R2, that does not equals to phi. Or third condition, the common attribute must be the candidate key of either R1 or R2 or both. So for lossless joint decomposition, it must satisfy all these conditions. If these conditions are not satisfied, we can say that the given decomposition is not lossless or lossy joint decomposition. So let us understand the concept with the example. So given a relation, एक table दी हुई है. In this, R is a relation. Attributes are A, B, C, D, E, or these are the tuples. State whether the following decomposition are lossless joint decomposition or not. So for first question, this R relation is decomposed into R1 and R2. Attributes are A, B, C, D. Now check for first condition, R1 union R2. That is A, B, C, D. In the R relation, there are A, B, C, D, E. E is missing. So first condition is not satisfied. So we can say that the given decomposition is not lossless. Now, second question, R1 ABC, R2 DE. So R1 union R2, A, B, C, D, E. First condition is satisfied. Now second condition, R1 intersection R2, that does not equals to phi. There should be some common attributes A, B, C, D, E. There is no common attribute. So second condition is not satisfied. So this is not lossless decomposition. Now check for third question. R1 union R2, A, B, C, D, E. First condition is satisfied. Now common attribute C is common. So that R1 intersection R2 does not equals to phi. So first condition is satisfied, second condition is satisfied. Now check for common attribute C. C is the common attribute. So C should be the candidate key of either R1 or R2. Now check for C. Candidate key means there is no same tuples exist in the table. So 1 and 1 same tuples exist for the C attribute. So we can say that the decomposition is not lossless because the common attribute C is not the candidate key of the table R. Now, fourth question. First, R1 union R2. A, B, C, D, E. Second, R1 intersection R2. Common attribute are A, C, D. A, C, D. Now check for third condition. Common attribute must be the candidate key. So at common attributes are A, C, and D. Or we can check A, all the tuples are different X, Y, Z, A. So all the combination X1P, Y2Q, Z1R, A35 all are different. So ACD is the candidate key or super key of the relation R. So we can say that the given decomposition is lossless decomposition. Now check for fifth question, R1, R2. R1 union R2 is A, B, C, D, E. That is satisfied. Now condition 2, common attribute. Common attribute is D. So that is not equals to 5. So second condition is also satisfied. Now D. D must be the candidate key. Check for D. D, B, P, Q, R, S. All the tuples are different. So we can say that D is the candidate key. So the given decomposition is lossless decomposition. So I hope you will understand the concept through this given relation. Now let us understand the lossless and lossy joint decomposition concept through functional dependencies. So schema R, V, W, X, Y, Z, and given functional dependencies are Z determines V and W determine Y, XY determine Z, V determine WX. Now state the whether the following decomposition are lossless joint decomposition or not. Now question number 1. R1 union R2, that is equals to R. So V W X then Y Z. This is V W X Y Z. Condition 1 is satisfied. Now check for condition 2. The common attribute is V. The common attribute is V. So that is not equals to 5. Second condition is also satisfied. Now check for third condition. The V is the common attribute. Now check V is the candidate key of either R1 or R2. Now take the attribute closure of V from the given functional dependency. From V, we can determine V. From V, we can determine WX. And from W, we can determine Y. Or from XY, we can determine Z. So from V, we can determine all the attributes given in the relation R. So V must be the candidate key. So V is the candidate key. So we can say that the given decomposition is lossless joint decomposition. Now let us take second example. Condition number 1, R1 union R2, that is equals to R V W X Y Z. Yes, it is satisfied. Second condition, R1 intersection R2, that does not equals to 5. The common attributes are X. So X, second condition is also satisfied. Now check for third. X must be the candidate key. So take the attribute closure of X from the given functional dependency. X to X, we can determine from X. We cannot determine anything else. So this is not the candidate key. So we can say that this condition is not satisfied. So we can say that the given decomposition is not lossless or lossy decomposition. So I hope you will understand the concept of decomposition. These are the references. Thanks for watching this video.